It seems like quantum computing is everywhere these days.
Oh, yeah.
It's hard to avoid it.
It's really taken off.
Yeah. Every week there's a new headline about some breakthrough or, a new milestone.
Yeah.
But it makes you wonder, when is all this hype going to actually turn into something useful?
Right. When do we see quantum computers actually doing something that makes a difference?
Exactly. When do we move past all the theory and see them actually tackling these big challenges in a way that lives up to all the excitement?
I think that's the real question, isn't it?
Yeah.
When does the potential translate into real-world impact? Because we're seeing this incredible race to harness quantum mechanics for computation.
Mm-hmm.
But you're right, it's that bridge between the science and the actual application.
Mm.
And it's not just about power, it's about practicality and cost.
Right. Can we actually use these things?
Exactly.
And that's exactly what we're diving into today.
I'm excited.
Yeah, because we've got a really fascinating collection of articles and information that gets to the core of this. So we're going to look at a major initiative that's trying to actually measure the progress of quantum computing. Put some metrics on it.
All right.
We'll see how quantum computing is being used to solve some really tough problems in chemistry.
Okay.
And believe it or not, we'll explore a way to analyze huge data sets using quantum-inspired techniques.
Interesting.
And we'll even get into what's being done to keep our data secure in a world with quantum computers.
So it's kind of a look at where we are now, how we're testing these capabilities, and what we're doing to prepare for the future.
That's our mission today.
Yeah, it's a great time to be looking into this because there's so much happening.
Absolutely. Okay, so let's jump right in with something really ambitious. DARPA's Quantum Benchmarking Initiative, or QBI. Now, DARPA, for those who might not be familiar, is the Defense Advanced Research Projects Agency in the U.S. They're known for funding some really cutting-edge tech.
Right, pushing the limits of what's possible.
Sometimes mind-bending stuff.
Absolutely. And QBI is a perfect example. They have a very specific goal: to figure out if quantum computing can reach what they call utility-scale performance by 2033.
2033, okay.
And what's interesting is their definition of utility scale.
Mm-hmm.
It's not just about raw power. It includes things like maintainability. How easy is it to keep running serviceability? Reliability. Can you actually manufacture these things at scale?
Right, so it can't just be this super powerful computer that needs a whole team of engineers to just to keep it on.
It has to be practical.
And costs a fortune.
Yeah, they're looking for something that can actually be used in the real world in a sustainable way.
Right, something that can be deployed reliably and practically.
And to do this, QBI is set up in 3 stages.
Okay.
Stage A, which they've just started, is all about coming up with a feasible concept for a utility-scale quantum computer. It's like the blueprint phase.
Okay, so this is the design phase.
Yeah, and they've chosen 2 companies to tackle this, Photonic and Quantinuum. Let's start with Photonic. They have a really interesting approach. They call it entanglement first. Entanglement first.
An entanglement, for anyone who needs a refresher.
Yeah.
It's one of those wild quantum phenomena.
It is one of the most bizarre things in quantum mechanics and really what gives quantum computing its power.
So what's unique about Photonic's strategy?
Well, they're really focused on distributed quantum computing.
Okay.
So instead of building one massive quantum chip, they want to connect lots of smaller quantum processors.
So like a network of smaller chips.
Right. More like a supercomputer made up of interconnected smaller units.
Okay.
And their entanglement, first idea emphasizes that they're starting by focusing on creating really strong, reliable entanglement.
Entanglement being that.
That connection between quantum particles.
Right, even when they're separated.
Yeah, spooky action at a distance.
Right.
They believe that's the key to building this distributed architecture.
That makes sense because if you're connecting all these separate processors, you need that entanglement to be rock solid.
You need that to be super strong and reliable. Historically, that's been a big hurdle. Keeping entanglement stable across large systems.
But it sounds like Photonic is tackling that head on.
They are. And they believe this approach could lead to systems that can scale up without being limited by the size of a single processor.
It's pretty clear that they're a Canadian company right outside Vancouver pushing the boundaries of this tech.
It is.
And Dr. Stephanie Simmons, their founder and chief quantum officer, she made a great point.
Okay.
She said that DARPA's focus on cost as part of the utility scale definition was a game changer.
Oh, yeah. That's a big shift. Because it means practicality is built into the goal from the very beginning.
Right.
It's not just about achieving the science.
Mm-hmm.
It's about making something that can actually be used.
And it's interesting that Krista Svor a technical fellow at Microsoft.
Okay.
She publicly supported photonics selection.
Oh, wow.
And specifically highlighted their approach to distributed quantum computing.
So they're getting some big name backing.
Yeah, when someone like Microsoft shows that kind of support, it really says something.
It definitely shows they see the potential there.
Yeah. Okay, so now let's talk about the other company that was chosen for stage a Quantinuum. They made a pretty bold statement.
Oh, yeah?
They said they already have the world's most powerful quantum computer.
That's a big claim.
That's not messing around.
No, it's not. But Quantinuum does have a pretty impressive track record.
Okay.
They were formed by merging Honeywell Quantum Solutions and Cambridge Quantum.
Oh, wow.
So they've got some serious expertise. And their roadmap is ambitious. They want a fully fault-tolerant quantum computer by 2029 and even bigger systems by the early 2030s.
So right in line with DARPA's 2033 target?
Exactly. Now, a fault-tolerant quantum computer means it can correct the errors that happen during quantum computations.
Because qubits are notoriously delicate, right?
They are incredibly sensitive to any kind of disturbance.
So if you can make a fault-tolerant computer, that's a huge step because it means you can run much longer and more complex calculations.
Exactly. And you can be confident that the results are actually accurate.
And Quantinuum seems very sure of themselves. Dr. Rajiv Hazra, their CEO, said they're confident they'll deliver on DARPA's objectives.
Okay.
That's a pretty strong statement in a field that's changing so rapidly.
It is.
Yeah.
And they're not working alone either.
Yeah.
Both Microsoft and NVIDIA are involved in their Stage A efforts.
So they've got some strong partnerships going on.
Yeah, it seems like they're building on existing collaborations.
So DARPA's not just handing over money and hoping for the best.
No, they've got this structured three-stage plan.
Right. Stage A for the initial concept, Stage B to develop a detailed R&D roadmap and figure out any risks. And then Stage C, where they'll work with the government to actually test and validate these concepts.
I'm sure they can actually be built and work in the real world.
Exactly.
Yeah.
And DARPA's made it clear they're going to have independent third-party assessments the whole way through.
Oh, that's crucial.
Right. It's about cutting through the hype and getting a clear, objective picture of what's possible.
Yeah, because there's always a lot of excitement around quantum computing.
Absolutely. So this is about really separating the real progress from just the claims.
Yeah.
Okay, so we've got a sense of how they're measuring the progress of quantum computing. Now let's look at a specific application chemistry. We found an article about a study at the Cleveland Clinic where they're using quantum computing to predict something called proton affinity.
Proton affinity.
Now, for those of us who haven't taken a chemistry class in a while,
Right, it's been a while.
can you remind us what proton affinity is and why it's a good test for quantum computers?
Sure. So proton affinity basically measures how strongly a molecule attracts and holds on to a proton,
Okay,
which is a positively charged particle.
right.
It's a really fundamental concept in chemistry. It affects tons of reactions and interactions between molecules.
Okay.
Now, this study looked at proton affinity in the gas phase.
The gas phase.
Which means the molecules are isolated, so you can see their properties without anything else interfering.
Okay, so it's like a pure measurement.
Right. Exactly.
But the article said that studying proton affinity in the gas phase is actually really tough using traditional experiments.
Yeah. It is. Yeah, there are a lot of challenges. For one thing, a lot of compounds don't like being gases.
Okay.
They don't evaporate easily. Or they might break down if you heat them up to turn them into a gas. And these experiments take a lot of time, and they're usually limited to small or medium-sized molecules.
So that's where computational methods come in.
Exactly.
Yeah.
And that's where quantum computing could be really helpful.
Because you can simulate these processes without the limitations of a physical lab.
Right. You can explore different scenarios and molecules much more easily.
So this team at the Cleveland Clinic, led by Dr. Kenneth Morris and Dr. Hani Jin, they didn't just use simulations on a regular computer. They actually used quantum hardware.
Wow, so they were working with a real quantum computer.
Yeah, and they combined machine learning with quantum circuits.
That's really cutting edge.
It is. So to understand why quantum computing might be good for this kind of problem, we need to go back to the basics.
Okay, back to basics.
What's the difference between a classical computer and a quantum computer?
All right, so classical computers use bits, which can be a 0 or a 1.
Right, the classic on or off.
Exactly. But quantum computers use qubits, which can be in both states at the same time.
Both 0 and 1 at the same time.
Yeah, it's called superposition.
So it's not just on or off, it's like a dimmer switch.
Yeah, that's a good analogy. It can be anywhere in between.
Okay.
Now, when classical computers calculate, they use logic gates that work on those zeros and ones.
Right.
But qubits are manipulated by quantum gates. which can do much more complex transformations.
So they can explore all those in-between states.
Exactly. And that's a huge advantage for something like chemistry, where you have tons of possible outcomes.
Because you can explore all those possibilities simultaneously.
Right, instead of one at a time like a classical computer.
Okay, so how did they actually apply this to proton affinity?
Well, they built what they called a quantum machine learning model, or a QML model.
Okay, a QML model.
Yeah, and they trained it using 186 different factors.
186? That's a lot of variables.
It is. But they used a quantum circuit to encode all that information into the state of the qubits.
Okay, so the circuit is like a way to represent all those factors.
Exactly. And then they adjusted parameters within that circuit using a machine learning process.
So the machine learning is figuring out the best settings for the circuit.
Right. They compared the model's predictions to real experimental results and kept tweaking the parameters until they got the best possible predictions.
So did it work?
It did. This hybrid quantum classical method was more accurate than just using classical computing.
Wow, so that's a pretty big deal.
It is. Dr. Merz even said that QML could eventually be more powerful than even supercomputers for these kinds of problems.
Really?
Yeah. And what's really important is that they used real quantum hardware, not just simulations.
So it's not just theoretical.
No, it's a real demonstration that quantum computing can make a difference.
This is really exciting for chemistry. Imagine being able to predict all sorts of reactions and properties.
It could completely change how we develop new drugs and materials.
Absolutely.
Yeah.
Okay, so we've seen how they're measuring progress in a real-world application. But there's another article I want to talk about. It's about a quantum-inspired way to analyze big data.
Quantum-inspired.
Yeah, it's the idea that we can use some quantum thinking even without a full-blown quantum computer.
Okay, that's interesting.
So some statisticians at Cornell have developed a new method for representing data.
Okay.
And it's based on ideas from quantum mechanics. But the cool thing is it can run on a regular laptop.
So you don't need a quantum computer?
Nope. It's all about using the math of quantum mechanics to our advantage.
Okay, so they're borrowing the concepts, not the hardware.
Exactly.
And what problem are they trying to solve?
Well, the problem is big data. We have these massive data sets that are full of noise and complexity.
Right, and it's hard to extract meaningful information from them.
Exactly. And traditional methods often struggle with that.
So how does quantum mechanics help?
Well, it provides a different way to think about relationships in the data. Classical statistics often focuses on probabilities of individual events.
Right.
But this quantum-inspired approach can capture more complex, high-dimensional relationships.
So it's like a more sophisticated lens for looking at the data.
Exactly. The article mentions something called intrinsic dimension estimation.
Oh.
Can you explain what that is?
Sure. So it's a way to figure out how complex a data set really is.
Okay.
Imagine you have a bunch of data points scattered in 3 dimensions, but it turns out they all lie on a flat plane within that space.
Okay.
So the intrinsic dimension would be 2, not 3.
So it's like finding the true underlying structure.
Right, exactly. But traditional methods for estimating this can be thrown off by noise and complexity.
So they don't always give you an accurate picture.
Right.
And this new method tries to overcome that.
Yeah, it uses quantum mechanics to simplify the data and filter out the noise.
So you get a clearer view of what's going on.
Precisely. And they built this model on something called quantum cognition machine learning, which is developed by a company called Cognitive. The idea is to move away from traditional probability theory and take inspiration from how humans think.
So building AI that's more human-like.
Exactly.
Interesting. And how did this model perform?
Really well. They tested it on different data sets, both real and artificial, with added noise.
Okay.
And it was more accurate and less affected by noise than traditional methods.
So that's pretty impressive.
It is. And where researchers Martin Wells from Cornell pointed out that this quantum aspect opens up a whole new set of mathematical tools.
That we didn't have before.
Right. And remember, we don't need a quantum computer for this.
It's all about using the math cleverly.
Exactly. We're getting some of the benefits of quantum thinking without the need for new hardware.
So we can start using these tools right now.
Exactly. It's a great way to bridge the gap while we wait for quantum computers to become more widely available.
It really shows that quantum mechanics isn't just about building fancy computers.
Right.
It's a whole new way of approaching problems.
A new way of thinking.
Okay, so we've talked about measuring progress, real-world applications, and even quantum-inspired tools. But there's another big piece of the puzzle we need to address: security.
Yes, the security implications of quantum computing.
Because if these quantum computers become powerful enough, they could crack the encryption we use to protect our data.
Right, that's a serious concern.
And it's not something that's decades away. It could happen within the next 10 years.
So we need to be prepared.
Absolutely. And there's an article about a company called Utimaco and their product, Quantum Protect, which addresses this threat. It points out that our current encryption methods, things like RSA and ECC, they're likely to become vulnerable to these future quantum computers.
So the security we rely on every day could be at risk.
Exactly. And that's why it's so important to start moving to called post-quantum cryptography, or PQC.
PQC, okay.
And NIST, the National Institute of Standards and Technology in the U.S.
Right.
They've been working on this. They've standardized some new algorithms that are thought to be resistant to quantum attacks.
So new ways to encrypt data that even quantum computers can't crack.
Exactly. And they've set a timeline aiming to have these new algorithms implemented and the old ones phased out by around 2030.
So we've got a deadline.
Yeah, we need to get this transition going.
So what is Utimaco's Quantum Protect doing?
Well, it's a package designed for their hardware security modules, or HSMs.
HSMs.
These are like super secure, tamper-proof devices for managing encryption keys.
Okay, so they're like the vaults for your keys.
Exactly. And Quantum Protect adds support for these new NIST standardized algorithms.
Ah, so it upgrades your vault to be quantum safe.
Precisely. And it includes support for some other quantum-resistant methods, too.
Like what?
Things like stateful hash-based signature schemes like LMS and XMSS.
Okay, and these are also thought to be resistant to quantum attacks.
Yeah, they use different math that's hard for quantum computers to solve.
So it's like having multiple layers of security.
Exactly. And the article mentions something called CNSA 2.0 compliance.
CNSA 2.0, what's that?
It stands for Commercial National Security Algorithms Suite 2.0. Okay. It's a set of algorithms that the U.S. government requires for certain applications.
Okay.
And Utimaco's Quantum Protect meets those requirements.
So they're meeting some high-level security standards.
Absolutely. And they've built in some really practical features.
Oh, like what?
Well, for example, they have a patented solution for managing those stateful hash-based signatures.
Okay, because those can be tricky to handle correctly.
Exactly. And it's field activatable, so you don't need to replace your hardware.
So it's an easy upgrade.
Right. But maybe the coolest thing is that Utimaco offers a free simulator for these new algorithms.
A simulator?
Yeah, so you can test them out in your own environment before you buy anything.
That's really smart, because these algorithms are still pretty new. Most people don't have much experience with them.
Exactly. So this simulator lets you get hands-on and see how they work with your specific systems.
Like a test drive.
Yeah, and Utimaco's chief security officer, Cindy Provin, called this crypto agility.
Crypto agility.
It's about being ready for the future and being able to adapt.
That makes sense. And did they mention any real-world examples of this being used?
Actually, yeah. Stefan Zimmerman, who's the head of NXP's Trust Provisioning Service, he said they used a pre-release version of Quantum Protect for secure firmware updates.
So it's already being used in the real world.
Yeah, it's a good sign that it's actually practical and effective.
It definitely shows they're serious about preparing for the quantum era.
Absolutely. Okay, so as we wrap up this deep dive, we've covered a lot.
We have.
We saw how people are seriously trying to benchmark quantum computing progress and figure out what utility really means.
Right.
We explored a real application in chemistry where quantum computing is showing real promise.
Yeah.
We even delved into these quantum-inspired tools for classical computing.
That was fascinating.
And crucially, we looked at what's being done to secure our digital lives in a world with quantum computers.
It's a lot to think about.
It is. It seems like the field is moving from theory to practicality.
Yeah, we're starting to see concrete initiatives and solutions.
And that shift is really exciting.
It is. It feels like the pieces are coming together.
Exactly. But we still have a long way to go.
Oh, definitely. Quantum computers aren't mainstream yet.
Not by a long shot. But the progress is undeniable.
It is.
So we'll leave you with this question, listener. Given all this rapid change, what unexpected opportunities or challenges might pop up in the next decade?
Oh, that's a good one.
And how will different industries need to adapt?
Healthcare finance materials, science, cybersecurity.
The list goes on. It's worth thinking about the bigger picture and maybe even exploring the areas that caught your attention today.
Definitely. This is just the beginning of the quantum revolution.
And it's going to be fascinating to see where it takes us.
I can't wait.